So this is a video about chapter 14, simple harmonic motion equations. Every time you hear the word simple harmonic motion, you should probably just think about a mass on a spring, and it goes back and forth and back and forth. If you want to think about a pendulum swinging back and forth, that's also simple harmonic motion, provided the amplitude is quite small. So these equations define the quantities that determine the motion. So we've got frequency and we've got period. So frequency is 1 over period. This is frequency, and these are all in the video, so I probably don't need to go into very much detail here. And then this is period, which is related to the time it takes to go back and forth once. And remember, one period is back and forth, back to where it started. Okay, now there's also an angular frequency, which is rads per second, which is 2 pi f. That's also just used to quantify the motion. Now, in order to have, for this spring, in order for that mass to go back and forth, there has to be something called a restoring force, and that is defined by Hooke's law. This is Hooke's law, Fx is negative kx. Now, we saw that in chapter 7 when we defined the elastic potential energy, which is directly related to this force. There's a negative because if the mass is moved to the right, the displacement x is positive, the force, so if that's x to the right is positive, the force is to the left. And so that's why there's this negative here in Hooke's law. And that's always the case. If you pull something away from equilibrium, you need to pull it back with a restoring force. That makes it oscillate. If this was a positive number, the thing would just accelerate over to the right and never go back. Okay, the next equation on your formula sheet has to do with the acceleration. So remember, when this mass goes back and forth, it's not going at uniform speed. It's slowing down, stopping, turning around, zooming, speeding up, then slowing down, turning around, speeding up. So the velocity is not constant, changes direction and magnitude, which means there is an acceleration, which is related to the springiness of the spring. Now this just comes from Newton's second law. If F net equals m times a, and the only force is the spring force, that's negative kx, is m times a, well, that's how you get that the acceleration is negative k over m times x. Okay, so acceleration, the further it is from equilibrium, the bigger the force, the bigger the acceleration. That's why these guys are proportional to each other. And they're in opposite directions. Once again, you pull to the right, force is left. That's why there's a negative here. Okay, similarly for the spring, you can relate the frequency of oscillation. Now, this is only for a spring. This does not apply to a pendulum. This is for the spring, because this is the spring constant. And so if you want to know what the frequency of oscillation is, depends how springy the spring is and how big the mass is. So you make the mass bigger, you make the frequency smaller. Okay, you make the spring constant bigger, and the frequency is higher, so it goes back and forth much quicker. Okay, and then you can just put these back into the formula for period and frequency. There's nothing new there. Now, from this equation, this is actually a differential equation, but you're not there yet with your math of differential equations. The solution to the equation gives you the position of the mass as a function of time. In other words, this equation, this is the answer. This is what physics is all about. This is the goal. This is where the mass is. So where is it? And this is the time, when. And where it is when depends on the frequency, the omega. It depends on how far to the side you pull it. So this is amplitude. So if you pull that mass way over to the right before you let it go, well, you've got a big amplitude, and its subsequent motion then depends on that. This phi, this just happens to be when you start your stopwatch. So if you pull the mass to the right, so it's at, this is 0, x equals 0, this is x equals a. So if you pull it here and then you say, okay, go, when you let go, you start your stopwatch, then in that case, the function that you have, x, would just be a cos omega t. There'd be no phi, because you're already at its maximum. And the reason it's a cos is because if you put t equals 0, cos of 0 is 1, x equals a. And here it is up here, x equals a at t equals 0. Now, if you decide to start your stopwatch somewhere else, like say maybe you pulled it aside over here to x equals a, you let go, it goes zooming back toward the middle, and at x equals 0, then you start your stopwatch. You go, oh, I'm going to start my stopwatch here at t equals 0. Well, then the function's a little bit different. You're 90 degrees out of phase now, so this function would be a sine function. In fact, it would be a negative sine function because you're going left. And when t equals 0, x equals 0. So here we are. But as t gets bigger, if I'm going left, then I need this negative sign. And so trying to figure out which function you're going to use for x, it all depends where you start t equals 0. And if you decide to start somewhere else in between, like say you decide to make t equals 0 somewhere in here, well, then you're going to have this phi, this phase constant. That just shifts the function so everything works out to where you hit t equals 0. Okay, now as this thing goes back and forth, as this mass goes back and forth, energy is conserved. And it is changing between kinetic and potential, kinetic and potential. And so E total is always kinetic plus potential. This equals a constant, like 100 joules. It starts with 100 joules, it's always 100 joules. It could be any constant. And it just so happens the constant has to do with when it's over here at x equals a, up here. When it's over here at x equals a, it's not moving, and so the kinetic is 0. And the potential is all elastic, half k x squared, which just happens to be 1/2 k a squared. So in general, wherever it is, it's 1/2 mv squared plus 1/2 k x squared is equal to a constant. And the total energy is divided among potential and kinetic all the time. If you just happen to be where v is 0, so this is at x equals a, v equals 0, and so E total would be 0 plus half k a squared, and that's your constant. So whatever that number is, that's the same number throughout. So if this is 100 joules, half k a squared, then kinetic plus potential always adds to 100. If you happen to be going at x equals 0, then you're passing through the middle. This is when you're going the fastest. This is v equals v max. And so now the kinetic energy, 1/2 v max squared plus 0 would be the same constant. It'd still be 100. This time, when you're going through the equilibrium, you're going the fastest. And then it could be any combination. So if this equals 100 joules, if I'm maybe, I don't know, 1/6 of the way along or something, this may be, I don't know, 80, and then potential will be 20. And it's always divided among kinetic and potential. Okay, the last equation here has to do with the simple pendulum. And so the period of a simple pendulum depends on gravity and is 2 pi root L over G. And it only depends on the length of the pendulum. It doesn't depend on the mass that you're hanging. Now, it has to be a small angle. If you don't have a small angle, it's not simple harmonic motion. It's a slightly different function that gets out. Okay, so that's it for the equations here.